230.4 worksheet. This is question 1. Says, refer to figure 230.271. Between the panel and the wireway, the minimum size circuit conductors for motor number 4 are blank og. Count the number of circuit conductors in the conduit and determine ampacity inside the conduit from the 90-degree column. So, we have a 208 volt, 3 horsepower, 3-phase motor. And remember, to find the code required FLA for that, we need to go back to table 430.250, and under 208 volts and 3 horsepower, it gives us 10.6 amps. We take that 10.6 amps, multiply it by 1.25, and that gives us 13.25, which we can round down to 14 gauge, or round down to 13 amps for 14 gauge. But that's just the bare minimum circuit conductor allowed for this circuit, not considering the other wires running inside that conduit. So what we need to do to take that into account is we have 12 conductors, so we go to table 310.15B3A, adjustment factors for more than 3 current carrying conductors. And in there, under 10 to 20 conductors, says we have a 50% D-rate value. So our wire is only good for 50% of the values given in the 90-degree column of 310.15B16. And this confused me for a while. I could never figure out why for questions like this we use the 90-degree column, but for basically everything else in these books we use the 75-degree column. It's because those columns are insulation ratings. The copper itself is rated for the 90-degree column there, but we're not allowed to exceed the lowest rated piece of the system, basically. So most of the time we're going to have breakers or some other kind of termination that's rated at 75 degrees or less than 90 degrees Celsius. And so we're not able to use that 90 degrees Celsius rating for our circuit unless it's been spec'd out by an engineer, which is going to be pretty rare. However, when we have D rating like this, we do get to start from the 90 degree column, as long as our answer comes out beneath 75 degrees, or in the case of small conductors, underneath the small conductor values given in 240.4D, I believe it was. So for that same, take that same 10.6 times 1.25 for 13.25, but then we need to multiply that by 2 because our conductors have a 50% D rate. So that'll give us 26.5, which rounds up to 27. And out of the 90 degree column, it looks like 12 gauge is good for 30 amps. So 12 gauge will be sufficient there. And 12 gauge is larger than our code required 14 gauge. So 12 gauge will be the correct answer for this one. Now, moving on to question 3. Refer to the information shown in figure 230.230. The motor is located 160 feet from the panel board, and the specifications limit the voltage drop to 3% at this motor. Use a K value of 10.86 and nameplate current to determine the proper size wire to satisfy the specs. So what we got to watch out for with questions like this, we get so used to following these code tables that are accounting for motors that we aren't actually installing. And this question is just asking for what size conductor we need to avoid going above 3% voltage drop. That has nothing to do with code requirements. That's just straight voltage drop calculations. So we're going to use the FLA given to us on the motor nameplate for this one. So, nifty thing to remember, the voltage drop formula. I'm never going to remember that off the top of my head. Right here in your Uglies book, it's page 50 on mine. I think I have a 2014, so if yours is 17 or 20, that might be a couple pages different. But you have voltage drop formulas for single phase and for three phase. And you can see both of them, they give it they give it to you whether you're looking for the actual volts dropped or for the circular mills, the size of the conductor, to keep within a certain voltage drop parameter. It's the same formula, just inverse. But so that formula, then in this case, it's 1.732 times K times length, one-way length, times I, or current, and then divided by voltage drop, and that's voltage drop in actual volts. So we take our 208, multiply it by 0.03 for 3%, and that gives us 6.24 volts. That's our volts dropped. Our K value is given to us in the question. It's 10.86. Our length one way is 160 feet, and you just keep it in feet for these voltage drop formulas given to us in the Uglies book. And then our current, or I, is 44.4, running at 208 volts, just based off of the motor nameplate information. So you take that 1.732 times 10.86 times 160 times 44.4, and then you get that answer and divide it by 6.24, and that should give you 21,414, and that is the conductor size that we need given in circular mills. So to get that into American wire gauge, we need to go back to, what is it? Here we go. Chapter 9, Table 8, Conductor Properties. And we look down here under circular mills and look for the first one that is over, what was it, 21,414. So it looks like 8 gauge is 16,510 and 6 gauge is 26,240. So 6 gauge is going to be the smallest conductor that will keep us under 3% voltage drop for this motor.